Gabriel Landi. I tried to have you, I don't remember when was it, a year ago or so, but with immigration, Canadian one or American one, both of them, yeah, it was a little bit difficult. So really my great pleasure now to have you to conclude to have the last talk, please.
Okay, thank you very much. Can anyone hear me? Yeah. Thank you, Devira, for the invitation. Thank you for the organizers. It's a pleasure to be here and a pleasure to be giving the last talk of this conference. So I was based in Brazil for most of my life, and I've moved to Rochester around a year and a half ago. I want to tell you a little bit of what we've been doing in our group since I got there. So essentially, the basic paradigm that I'm going to be thinking about is essentially, the measurements and the data that we get when we measure a quantum system. So I'll take, this approach that we never really see a quantum system, right? No one's ever saw a quantum system ever. All we see is data, right? You measure it and you get some data out of it. And so essentially we have bit strings of data, and we have to think about what can we learn about the quantum system based on these bit strings of data, right? I will take here the following approach to measurements. I will always be thinking about measurements as essentially an interaction of the system with a probe or an ancilla, right? And so a measurement can always be thought of as an ancilla that comes in, interacts with the system, becomes essentially correlated with it, and then we measure this ancilla and we get a data point out, okay? And this is nice because it naturally encompasses this kind of interplay between information gain and back action, right? Because the stronger the ancilla interacts with the system, the more you gain information, but also the back action is stronger. Now, my interest here will actually be in continuously measured quantum systems, right? So essentially, instead of thinking about the usual prepare and measure protocol, I'll think about a single quantum system that is constantly being measured. So the idea, you can always picture this kind of measurement as what we call essentially a collision model, which is you have a system, interact with the ancilla, get one data point. Then you throw this ancilla away, you bring in a fresh new one, interact again, get a data point, and so on. Right? And then if you do this, you get essentially your bit string of data, right? A single shot and the single realization of your experiment for a single preparation of the system, you just measure and get a data string. Now, I wanted to emphasize the connection that this has with hidden Markov models, right? So a hidden Markov model essentially involves a hidden layer, something that you cannot see, in this case, the quantum system, and then a visible layer, which is the emitted symbols, the things that are emitted from this hidden layer. So in this case, the data points, right? So we never really see what's going on in here. All we see is the visible layer. Okay, let me actually emphasize a bit more this connection with hidden Markov models. So a hidden Markov model, classical one, yeah, it's essentially described in this way. You have some kind of state space, in this case A, B, and C, that the system can jump. And every time the system jumps from one state to the other, it emits a symbol. In this case, the alphabet of symbols is 0 and 1, for example, right? And a hidden Markov model is completely specified by a joint probability distribution that the hidden layer transitions from sigma prime to sigma, and at the same time emits a certain symbol x. So if you write down this probability distribution, you specify a hidden Markov model. Now, if we want to simulate, say, in a computer, this hidden Markov model, here's how we would do it. You start with some prior distribution about your knowledge about where the system is within this layer, and this could very well be a uniform distribution if you don't know anything. And then you sample the next symbol, x, right? Now, and so you choose a x randomly, and once you chose this, then you can update, you can do a Bayesian update of the state of your hidden layer, given your observation, right? So this is just Bayes' rule. And instead of having a prior, which didn't have any information, now you gain a bit of information, so you update your probability distribution. You update your knowledge about where the system is in this hidden layer based on this bit that you obtained. And for reasons that will become clear in a second, we can write this in a more convenient way. So we have this kind of object with 3 indices, and what we can do is we can build matrices. So for each emission x, we build a matrix with symbols sigma, sigma prime. We build a vector, which is just a bunch of ones, and a vector, which is just the probability distribution, this pi. And then this formula becomes this kind of sandwich, one of this matrix mx pi, And this update becomes essentially the application of this matrix mx to pi, right? So this is a slightly more elegant, I guess, way of making this kind of hidden Markov model more systematic. Now, why is this useful? Because we're going to be thinking about a general setting of quantum instruments, right? So this entire process here, the fact that you bring in an ancilla, you make it interact with your system, and you measure the ancilla, if you think about this usually in what we call the Stein spring dilation kind of ideas, this can be thought of as an instrument, which is essentially now not a matrix like before, but is a super operator, which acts on a density matrix, right? So these formulas are almost identical to the ones I wrote before, where your state is now a density matrix, your action of your measurement is this instrument mx, and essentially to calculate the probability, you take the trace, and to evolve, you essentially apply this instrument to the state rho, right? So this kind of evolution tells you how should we update the state of the system, given our knowledge that a symbol x was emitted. What is interesting about quantum systems that is usually not present in classical systems is that we have the back action, right? And so this means that if we were to measure, but we forget the result, we just don't write down what symbol x we obtained, we still get a non-trivial dynamic. So the state of the system, we have to kind of calculate, this just average over all of these states with the probabilities. We still get a channel here, which is still going to affect the density matrix of the system. So the fact that we know that the measurement happened, even if we don't know what was the outcome of the measurement, is still we still need to update the state of the system. So this is the back action right here. Okay, so before I actually go to more concrete examples and I leave this kind of very abstract picture, let me just again explain real quickly how we would, for example, simulate this in a computer. So we start with some generic state rho 0. You sample your first bit x1 with this kind of probability because you have your set of instruments here. And once you get your x1, you update your state by applying the instrument to the initial state. And then you sample a second state, which is now sampled from a conditional probability distribution, right? It's sampled from a x2 given x1 because everything is a single shot like stochastic, right? So you obtain x1 in the first round, so now you sample x2, you update again, and so on and so forth. So continuing this way, you obtain your bit string of data. I'll usually, I use this kind of notation to denote that when convenient, like 1n to mean, the string from 1 to n. And these are essentially the formulas that you would need. So if you want to calculate the generic probability distribution of observing a trajectory, it's just applying your instruments over and over again, and you get what you want. And this is the formula for the conditional state. Okay. Now, here's a more concrete example of the same thing. And this is a quantum jump unraveling of a master equation. So suppose you have the evolution of a quantum system, which has a unitary Hermitian part, and then a dissipator with a jump operator L. Now, it's been known for many decades that you can interpret this kind of open evolution as something that is split into jumps and no jumps. So the idea is that most of the time the system is evolving kind of smoothly, but every once in a while there is essentially a sharp transition, which is essentially an excitation that is kind of leaving the system towards the path. And this is what we call the quantum jump. So the instruments in this case, to give you a more concrete example, would be essentially the jump instrument, which is you apply L and L dagger to your density matrix, and the no jump instrument, which is a small update of the state. So it's like rho plus dt times a small update. So most of the time, what's actually going to happen is that the system is going to evolve under no jump, right? Because the probability of this thing to happen is proportional to the time step dt, and which is very small. So most of the time, actually nothing happens. The system just evolves smoothly, and then every once in a while, boom, there is a jump, right? So this is one way of kind of writing down this framework. Now, something which I personally find much more interesting is the fact that you can have quantum jumps with multiple channels. So to illustrate this, I put here this picture from this paper by Andrea Hoffman on quantum dots, right? So what they do here is they have a little dot in the sample right here, which can hold a 0 or 1 electrons. And electrons can tunnel from essentially these leads, these wires, into the dot or back. right? And they can monitor continuously the population of this dot. So they do this by analyzing this kind of current through here. I realize that maybe the color scheme here is not very good, but essentially the current that is flowing through this kind of passage is, if you look at it, it's going to behave somewhat like this. So it's up and down and up and down, right? Every time it goes up, it's an injection jump. It means an electron tunneled from the bath to the system. And every time it goes down is an extraction kind of jump. So this is a situation where you have two types of channels, right? Two flavors of quantum jumps, an injection kind of jump and an extraction kind of jump, right? So the way I like to think about this is as essentially, you know, when you're playing like video games like Guitar Hero or any kind of video games, because you have these different buttons, right, that are different symbols, and they also occur at random times. So a quantum trajectory in this case is really a set of symbols and time tags. Is, you know, the jump that clicked and the time tag of when that clicked occurred. So that's essentially how the trajectory in the quantum jump unraveling is made up. Now, I wanted to make a brief kind of more technical comment, which is that when we're talking about quantum jumps, there are actually two ensembles, two ways of thinking about quantum jumps, which are not equivalent. One, which is the more kind of natural one, is what we call the T ensemble. And that is an ensemble where you assume you have a fixed time. So, you know, you look at your system for a fixed amount of time. And therefore, the number of jumps that you get during that time can fluctuate as a random variable. But you could also think about another ensemble where you fix the number of jumps that are going to happen. That's what we call the N ensemble. But now the time where the system is going where the last jump essentially is going to happen is a random variable. And in this N ensemble, you can think about instruments that are described in terms of actually two data points, a time, tau, and your jump channel X. So we can write down, I'm kind of skipping a little bit here of the kind of mathematical details, but the idea is that you can write down instruments that describe a jump happening in channel X at time tau, right? And so now that we have these two symbols, we can even do something else, which I personally find kind of nice, which is you consider quantum jumps without time tags. So suppose, you know, your jumps are happening, and you know the sequence of symbols that you're observing here, but you don't know exactly when they're happening, either because you don't have a good clock or because maybe for whatever reason you don't care, right? So we integrate, we marginalize over the times, and we just get a process where we're just looking at the statistics of the symbols that the system emits. Okay, so let me give you a classical analogy to kind of explain what I mean. Suppose you have a system, which I'm going to pretend is a lattice with 4 sides. Each side can take only 1 particle. And suppose that I can monitor that a particle comes into the lattice from the left, which I call an IL jump, or I can monitor that the particle is extracted to the right path. So these are the processes that that are visible to me. This is all I can see, right? So this is now a sequence of events that could happen in this classical lattice. In the first step, maybe an a particle comes in. Then in the second step, this particle might move around here as well. And then in another step, maybe this particle is here, but a new one comes in, and so on. And at some point, maybe, for example, this one leaves, and so on. So you have this kind of internal dynamics. You're blind to all of this. All you can see are these kind of arrows here on the border. So for this entire sequence of processes, all an experimentalist would see is just these 3 symbols, right? Injection, injection, extraction. That's it. And then the question is, what can you learn about the system if this is all you know, right? What kind of information can you learn if this is the only thing that you can actually observe? Okay, so why do we care about this, right? Why is this relevant? Well, one argument is because this gives you some predictability, right? Imagine you're trying to predict future symbols. You're trying to predict what's going to happen in the future, right? If you know exactly the state of the system, then you can make statistical predictions about what's going to happen. So in general, if you want to make a guess about the next state of the system, this will usually require that you keep track of all of the past emissions. However, if you know that the system is in a specific density matrix, this is a kind of a data compression, right? You don't need to know an entire sequence of symbols. All you need to know is the internal state of your model, and this will give you the correct probabilities for future predictions, right? So in the HMM literature, this is called a mixed state representation, which is kind of a confusing name because the mixed state here has nothing to do with density matrices. It's a terminology from classical literature. Yeah. And I mean, this might sound a bit silly, but you can even make, there are people now trying to apply some of these ideas to, say, large language models, right? So for example, you have ChatGPT and it's spitting out words and it has its own internal state. So, we can make a Bayesian estimation of what is the internal state of your model, given that it spit out certain words. And why is that relevant? Because that would allow you to predict what are the next words that it's going to spit out. Okay, so now let me show you an example of what you get if you try to do this for a quantum model. So essentially, this is again a lattice, right? So, but the only difference is that instead of imagining that the particles can hop, I'm actually gonna, assume these are fermions that can tunnel, in like a tight binding kind of model, so they can tunnel between lattice sites. Now, this kind of little diagram essentially tells us where is the system after a jump, right? So this is the state of the system after each kind of jump occurs. So if you have a lattice with one side, it's pretty intuitive. If the lattice, for example, is empty and you get an injection, so injection is red, right? If you get an injection, you go to state one. That's pretty easy. And then if you get an extraction, you go here. And in this case, these are the only possibilities. A particle comes in, goes out, comes in, goes out. That's all that can happen, right? Now, if you have two lattice sites, then here's a little bit how it works. You start empty, and because you're tunneling, from the left, if an injection occurs, you go from 0, 0 to 1, 0, right? Now, from here, you actually have two possibilities. You can either gain another particle, 1, 1, or you can actually emit a particle. Notice that both of these processes, they implicitly require that something happens inside the lattice. Because, for example, if you want to have another injection to go from here to here, this site here is occupied. But what happens is that as soon as you observe a jump, this particle at state one is going to start kind of tunneling to the other sites and moving around through this kind of unitary dynamics and giving some room to another particle to actually come in, right? And the same thing is for, say, this particle to be emitted. So the transition from 1, 0 to 0, 0, because we're extracting from the right side, this would actually require this particle to essentially tunnel to the neighboring site until it's eventually extracted out, okay? Okay, and this is all nice and it's all very intuitive, but now let me tell you what happens if you have three lattice sites. I personally find this a little bit surprising and interesting. So again, suppose your lattice is empty and you inject a particle. Then with certainty, you go to the state 1, 0, 0. Now you inject another particle and you go to a state which is a subspace of your Hilbert space that has exactly two particles. So the number of particles here is fixed. However, this state is not a simple state. It's in general, it will have coherences and so on, because you have this kind of competition between jump dynamics and unitary dynamics. So this will be a kind of more complicated state with some coherences. And now from this state, you can always reset by actually obtaining another particle. So that the kind of the points with the little stars are like resetting states, right? So if you come here to 1, 1, 1, then the whole thing completely resets. But what is more interesting is this. Suppose you have two particles and then you emit a particle. Then you go into another subspace, which with certainty has one particle, but is again a state that is not diagonal, it's a state with coherences. And then, of course, things are random, you can go either way, but if you keep going back and forth, and this is the important bit, you go between these two subspaces, but you don't go back to the same state. So the state here, so if you go here, then here, you're not back to the same state. You keep actually moving around this Hilbert space to a bunch of different states. And I wanted to try to illustrate that. I'll play a silly movie here where I'll show the actual density matrix of the system. And there's going to be a string of bits that you obtain here. So let's see if this works. So I'm using actually exact algebra just to emphasize that it's not an approximation error or something. These are really fundamentally different states. So you see that every time you observe an emission or an injection, the state is actually fluctuating. These are all completely different states, okay? So essentially the system, the states that the system traverses here actually never repeat. So the analogy is somewhat the following. So, when you have discrete state spaces, the system will usually have, certain configurations, A, B, C. And when you have, say, Brownian motion, like, or some kind of Langevin equation stochastic process, usually the state of the system is a real variable and it's just kind of moving around continuously, right? With Hilbert space, you can actually have both. You can have kind of corners of Hilbert space where the system is essentially behaving like a discrete level model, and corners of Hilbert space where it's behaving kind of more in a continuous way because it's kind of navigating these subspaces in more complicated ways. And this is what this model is showing. Cool. So now what I wanted to discuss is some results by Abe, who's here in the audience and also presented a poster, where we apply some of these ideas and we take them a lot further to understand patterns in thermal machines, right? So essentially introduce some thermodynamic flavor into this kind of discussion. So this is the usual drawing that you'll see for the operation of thermal machines. The drawing on top is what we would call a heat engine, right? So in a heat engine, there's a hot bath, you get some energy out of it, and then you extract some work from this and you dump your excess into a cold bath. The one on the bottom is a refrigerator. Essentially, you need to input some work, and with this work, you can actually pull heat from the cold bath towards the hot bath, right? That's the idea. Now, if we try to unravel this in terms of quantum jumps, we might intuitively consider these two processes. So what we might imagine is an engine cycle is, say, an injection of particles from the hot bath and then extraction to the cold one. And a cooling cycle would essentially be the opposite, the other way around, right? Of course, if we want to allow for all possibilities, right, because, for finite temperatures, if a process this way is possible, then the kind of the opposite way also has to be possible. There's also always going to be what we call these idle cycles, which is essentially, an excitation comes in from the hot bath and then it's spit out back again to the hot bath and nothing actually useful happened. So this is what we call an idle cycle hot and an idle cycle cold. Right? Now, this kind of idea of unraveling the operation of a thermal machine in terms of cycles, I think it's really nice. I think it's really powerful. It gives a lot of insight into essentially, how these things operate in this mesoscopic or microscopic regime. However, there's a difficulty to this, which is, if all you're given is a string like this, how do you identify a cycle, right? So this is all you have, just the string. How do you read a thermodynamic cycle from this? Well, the problem is that in general, this can't really be done. And this substring here, I think, illustrates the idea. Suppose you have, injection cold, injection hot, extraction cold. What does this mean? Well, it could mean, an injection cold with an extraction hot, and this would be essentially a cooling cycle. It would be this process. And this is kind of, intercalated with an injection hot and extraction cold, which would be an engine cycle. But this could all, excitations are indistinguishable. So this could also very well be an injection cold, extraction cold, which is this kind of idle cycle, nothing happened, and an injection hot, extraction hot, which means also nothing happened, right? So at least the way we phrase it like this, I don't think the identification of cycles is really possible if all you get is this kind of string. So the first thing that we try to work out is, okay, so, given a slightly general class of master equations, when is it going to be that we can identify cycles? And what we concluded is that for that to be possible, the system has to essentially have, at any given time, at most one excitation. So essentially, there's some excitation that goes in, some excitation that goes out. The bit string that you get has to be perfect, kind of alternating injections, extractions, injections, extractions. There's still a lot of stuff that can happen with this. At first, we thought this was maybe kind of restrictive. Of course, there are experiments that do this, like double quantum dots, they do this all the time. It's not far from experiments, but we thought maybe from a modeling perspective, this could be a bit restrictive, but we learned that no, there's actually quite a large class of very interesting models that we could come up with that satisfy this kind of principle. So the first result that Abe showed was that for this to be possible, essentially for the system to have a single excitation, your Hilbert space has to be split into two, right? There's what we call the post-injection subspace and a post-extraction subspace. Essentially, every time an excitation comes into the system, it has to live on this corner of Hilbert space. Every time an excitation goes out, it has to live on this corner. in between quantum jumps, it can do a lot of stuff in these corners. It can extract work and so on. So there's a lot of dynamics that can go on in here. But every time there is an injection or extraction, it has to switch from one part of the Hilbert space to the other. So the nice thing about this is that it allows us to convert a bit string of jumps into a bit string of cycles. Now, all processes are injection, extraction, and so on, which means that we only need to consider the 4 possibilities, which is, well, we weren't very creative with this, so we just called them 1, 2, 3, and 4. But essentially, it's an engine cycle, a cooling cycle, idle hot, and idle cold. Right? These are the 4 possibilities of thermodynamic cycles that can happen. But this is super nice because now that we have this identification of these cycles, we can ask a lot of questions that I find really, really meaningful. We can ask, for example, what's the probability that each cycle is going to happen? And what's the probability that each cycle might take a certain time, right? So are some of these cycles quicker than others and so on? We can ask these kinds of questions. We can talk about correlations between cycles. So we can say, if you observe a hot cycle, what's the probability that the next one is going to be a cold cycle? This is kind of very reminiscent of bunching and anti-bunching in optics, right? Where you say, well, there's an emission, what's the probability that the next one is going to happen, and so on. It's kind of the same idea, but now thinking in terms of cycles, correlations between cycles. We can talk about, again, the time or the average time to complete cycles. And we can talk, most importantly, about the notion of intermittency, right? In between useful cycles, how many times is your machine actually doing something useless? Right? Because this doesn't give you anything, right? So it could very well be that once you resolve your machine in time and you resolve your machine in cycles like this, most of the time it could very well be that your machine is just doing useless stuff, and then every once in a while it does something useful, right? So you can define the idea of intermittency of a machine. How often is it actually producing useful thermodynamic output? One of the nice things that we show, kind of complementary to all of this, is a connection with known steady state properties, in particular, the average current of excitations, which is what is usually employed to characterize the steady state of operation of these machines. We show that it's the difference in the probability of observing an engine cycle and a cooling cycle divided by the time, the average cycle time. So this is kind of intuitively what you would expect. It's a current, so it's essentially, there's something related to how often cycles happen, and essentially the sign of the current, if the current is going this way or this way, like, sorry, a little bit like, if it's going to be like this or like this, right? It's essentially going to be determined by how likely each of the cycles are to occur. Okay, here are some examples for a 3-level maser, which is a widely used example in quantum thermo to describe these kinds of machines. So this is a model with 3 levels. We assume that the hot bath can couple levels 0 and 2, and the cold bath can couple levels 2 and 1. Now, the coupling between levels 1 and 0 is a unitary coupling. It's essentially, the emission or absorption of photons through a cavity, for example, right? So this is the thing that does work. Work for this model is essentially emitting a photon. So this is essentially the model of a maser, right? And the masing effect is essentially work. Now, in this case, here are the cycles, right? So you have the kind of hot cycle, engine cycle that goes this way, the cold cycle that goes this way, and the 2 idle cycles like this. And so here is an example of what you would get for the probability of observing a cycle of type X of flavor tau, right? So this is a waiting time probability, waiting time distribution, but now resolved in each specific cycle, right? And so you can see, what are the typical time scales of the cycles, and also, what are the typical heights of the cycle. So if you were to integrate this curve over time, this will give you the probabilities of observing each cycle type, yeah? So this is actually what we plot here. So I guess the color scheme here is not very clear, but if you look at the TV, so essentially this line defines the regime where the machine is operating as a refrigerator or as an engine. And you see, for example, that in the entire regime where it's operating as a refrigerator, the cycle of type 2, which is the cooling cycle, is more likely than the cycle of type 1. So that's good. First, that it has to be like this. But we also see that the most likely cycle of all is just the idle cold cycle, which is the useless one. So it's actually always more likely to find the system doing, a useless cycle. We can also calculate times between cycles and see, is one cycle type faster than the other, and so on. So these are like conditional averages, is the average time a cycle takes, given that the cycle is of this type or that type, right? So it tells you about the speed of each cycle. And this, I mean, these kind of things, I mean, this is a very simple model, but you can also go to more complicated models. The formulas that Abe derived are all kind of very general, and therefore there are quite a few models that we can play with, and that's exactly what we're doing right now. So I reached the end of my talk. So I just wanted to conclude by saying that if you continuously measure a quantum system, you get a time series. You get a random stochastic time series of data points. And there's a lot of information in this time series. There's very complicated correlations in time and so on. And you can use this to learn a lot about your quantum system and about what's happening. So I tried to show you two examples. One was the this idea of how the system moves about in Hilbert space, the kind of corners of Hilbert space that the system occupies. And the second one is this idea of how we can resolve the operation of these quantum thermal machines in time and resolve them in cycles. So these are the basic references that I talked about today, and be happy to answer any questions. So, thank you very much.